The cockpit glass shattered as anti-aircraft fire ripped through the fuselage. Flight Lieutenant Ronald Harker could feel the vibrations of his Spitfire changing, the engine note dropping, the altimeter falling. Somewhere over occupied France, with nothing but the cold Channel waters between him and England, his life depended entirely on a 27-liter piece of British engineering, the Rolls-Royce Merlin. He nursed the throttle, coaxing every remaining ounce of power from the wounded machine. And as the white cliffs of Dover finally appeared through the haze, Harker made himself a silent promise. This engine, this magnificent creation of steel and aluminum and pure genius, would not just save lives, it would change the entire course of the war. What Harker could never have imagined, as his damaged aircraft limped home that day, was that his future would be intertwined with one of aviation history's greatest controversies. A story of British brilliance, American industrial muscle, and a technology transfer that some would call collaboration, and others would call theft. This is the untold story of the Merlin engine, the heart that beat inside the Spitfire, the Hurricane, the Lancaster, and ultimately America's greatest fighter, the P-51 Mustang. It is a story of genius and desperation, of politics and pride, of how one nation's greatest invention crossed the Atlantic and helped another nation claim victory as its own. If you find yourself drawn into this incredible chapter of history, consider subscribing to this channel, because what you are about to discover will change everything you thought you knew about World War II. The origins of the Merlin can be traced to a single man. Sir Henry Royce was not born into privilege. He entered this world in 1863, the son of a miller who died when Henry was just 9 years old. Poverty forced him to sell newspapers on the streets of London at the age of 10. He received barely a year of formal schooling, yet within that small, determined frame lived one of the most brilliant engineering minds the world would ever know. By sheer force of will, Royce educated himself, apprenticing as an electrician, studying mechanics in his spare hours, absorbing everything he could about how machines worked. In 1984, Royce purchased a French Decauville automobile. Most men would have simply driven it. Royce took it completely apart. Every gear, every bearing, every component was examined, measured, and found wanting. Within months, he had built his own car from scratch, correcting every flaw he had identified. That car caught the attention of Charles Rolls, a wealthy aristocrat with a passion for automobiles and a showroom in London. Their partnership, formalized in 1906, would create one of the most legendary brands in industrial history. But Royce's perfectionism extended far beyond luxury cars. When the First World War erupted, Rolls-Royce turned its attention to aircraft engines. The Eagle engine, designed under Royce's direction, powered the Vickers Vimy that made the first non-stop transatlantic flight in 1919. Victory demanded better engines, and Royce was relentless. His philosophy was simple, yet profound. Accept nothing, question everything, make it better. His engineers knew that any design submitted for his approval would be returned covered in pencil marks, annotations demanding improvements they had not even considered. The seeds of the Merlin were planted in the late 1920s when the International Schneider Trophy air races became the ultimate proving ground for aviation technology. These were not mere competitions. They were statements of national pride, engineering contests where the fastest seaplane would crown its nation as the leader in aeronautical advancement. In 1929, Britain won with an aircraft powered by Rolls-Royce. But the 1931 race would be different. It would require something revolutionary. Royce, now in his late 60s and working from his home in West Wittering, due to failing health, sketched designs in the sand of the nearby beach. His vision was for an engine capable of producing over 2,000 horsepower, more than double what any existing power plant could deliver. The R engine, as it became known, was a masterpiece of concentrated power. when Supermarine's S-6B seaplane screamed across the finish line at over 340 miles per hour, setting a world speed record. It was Royce's engine that made it possible. That victory was not just about a trophy. It demonstrated to the world that Britain possessed engineering capability beyond anything its rivals could match. From the R engine came the blueprint for something even more important. Royce understood that racing engines, designed for short bursts of maximum power, were useless for military aircraft. What the Royal Air Force would need was an engine with the R's potential for power, combined with the reliability to run for hundreds of hours without failure. In October 1933, just 6 months before his death, Royce approved the final designs for a new engine designated the PV-12. The letters stood for Private Venture because the Air Ministry, in its short-sightedness, had not ordered such an engine. Rolls-Royce was betting its own money on the future. The PV-12 first ran in 1933. By 1936, it had been renamed the Merlin, after the small Falcon, not the Wizard of Legend. The engine would undergo constant refinement over the following years. Early versions produced around 1,000 horsepower from 27 liters of displacement. 12 cylinders arranged in a V configuration, liquid-cooled, supercharged. But those specifications only hint at the sophistication within. Every component represented years of accumulated expertise. The crankshaft was machined from a single forging of the finest steel. The connecting rods were polished to remove any microscopic imperfection that might become a stress point. The supercharger, which forced additional air into the combustion chambers to increase power at altitude, was designed with tolerances measured in thousandths of an inch. What made the Merlin truly remarkable was its capacity for growth. Royce had designed flexibility into its architecture. While the basic dimensions remained unchanged, nearly every internal component would be improved, strengthened, and refined over the following decade. The Merlin that entered service in 1938 was powerful. The Merlin that emerged at war's end was transformative. The summer of 1940 brought Britain to the edge of extinction. France had fallen. The British Expeditionary Force had been evacuated from Dunkirk, leaving most of its equipment behind. Hitler's Luftwaffe possessed numerical superiority and combat-tested pilots. All that stood between the German war machine and total control of Western Europe was a thin line of young British pilots and the machines they flew. The Battle of Britain was not just a military engagement. It was a technological contest, and at the heart of that contest was the Merlin engine. Fighter Command deployed 2 primary aircraft against the German onslaught, the Hawker Hurricane and the Supermarine Spitfire. Both were powered by the Merlin. The Hurricane, designed by Sidney Cam, was the workhorse of the battle. It was easier to manufacture, simpler to maintain, and could absorb tremendous punishment. Its fabric-covered fuselage could be patched in hours, allowing damaged aircraft to return quickly to combat. By July 1940, 32 squadrons flew Hurricanes. The aircraft would account for 60% of all German losses during the battle, shooting down 656 enemy aircraft. The Spitfire, designed by R.J. Mitchell, captured the public imagination. Its elliptical wings and graceful lines made it an icon of British resistance. It was faster and more maneuverable than the Hurricane, better suited to engaging the Messerschmitt Bf-109 escort fighters. Fighter Command doctrine typically sent Hurricanes against incoming bomber formations, while Spitfires tangled with the fighter escorts above. This division of labor played to each aircraft's strengths, but both aircraft shared the same beating heart. Without the Merlin, neither could have survived against the German onslaught. The pilots who flew these machines operated under almost unimaginable pressure, scrambled multiple times daily. They would climb to altitude, engage formations sometimes numbering hundreds of aircraft, and fight for their lives in combats that lasted minutes but felt like hours. The Merlin's reliability became a matter of life and death. An engine that could be pushed beyond its rated limits in emergencies. An engine that would not fail when a pilot needed one last burst of power to escape a pursuing German fighter. An engine that could bring a wounded aircraft home across the channel when every other system had failed. The Germans could not understand why their bombing campaign was failing. Their intelligence had assured them that fighter command was nearly destroyed. Yet every day, more Spitfires and Hurricanes rose to meet them. What the Germans did not realize was that British production was outpacing their destruction, and at the center of that production miracle was the Merlin. Rolls-Royce's Derby factory was producing engines at unprecedented rates, supplemented by shadow factories in Crewe, Manchester, and Glasgow. Every available resource was directed toward one goal: keep the engines flowing to the squadrons that needed them. One man deserves particular credit for the Merlin's performance during this desperate summer. Stanley Hooker was not a typical Rolls-Royce engineer. He was a mathematician recruited directly from academia in January 1938 after an interview with Ernest Hives, the company's managing director. Hooker was given unusual freedom to examine any aspect of the company's work that interested him. He quickly gravitated toward the supercharger department. What Hooker discovered appalled him. The superchargers fitted to the Merlin were operating at roughly 68% efficiency. Through careful mathematical analysis and application of aerodynamic principles that the original designers had not fully understood, Hooker calculated that significant improvements were possible. His recommendations were incorporated into the production line for the Merlin 45, increasing efficiency to 76%. That 8 percentage point improvement translated to a 30% increase in power output. When the Merlin 45 entered service in the Spitfire Mark V in October 1940, it gave British pilots a decisive advantage in the crucial final stages of the Battle of Britain. But Hooker was already looking further ahead. The Air Ministry had requested a turbocharged Merlin for high-altitude operations. Hooker rejected the turbocharging approach entirely. Instead, he proposed something more elegant: a two-stage supercharger system that would provide exceptional performance across a wide range of altitudes. The concept was brilliant. Two impellers mounted on a common shaft within a single housing would compress the incoming air in sequence. Between the stages, an intercooler would reduce the temperature of the compressed charge, increasing its density and therefore the power potential. The engineering challenges were immense. Temperatures within the supercharger assembly could exceed limits that would destroy conventional materials. The rotating components had to spin at tremendous speeds while maintaining perfect balance. The intercooler added complexity, weight, and potential failure points. Hooker attacked each problem methodically, applying his mathematical background to optimize every parameter. The result was the Merlin 61, which first ran in April 1941. When the Merlin 61 was fitted to the Spitfire Mark IX, the results were dramatic. The new variant could climb faster, reach higher altitudes, and outperform the dreaded Focke-Wulf 190 that had recently appeared over Europe. The Merlin 61 gave British pilots the ability to fight at 30,000 feet and above, altitudes where single-stage supercharged engines simply could not compete. Hooker's quiet genius had delivered exactly what the Royal Air Force needed, exactly when they needed it. Yet even as British engineers performed miracles, a stark reality confronted the war planners in London. Britain alone could not produce enough Merlins to meet demand. The engine was needed for Spitfires, Hurricanes, Lancasters, Mosquitoes, and numerous other types. Every shadow factory was running at maximum capacity. The only solution was to expand production overseas, and that meant America. The story of how America came to build the Merlin involves one of the war's most controversial figures. Henry Ford had created the modern automobile industry. His assembly line techniques had revolutionized manufacturing. In 1940, His factories represented the greatest concentration of production expertise in the world. Lord Beaverbrook, Churchill's Minister of Aircraft Production, approached Ford with a proposal. Britain would provide the designs, the technical expertise, and the initial funding. Ford would build 6,000 Merlin engines for the Royal Air Force and another 3,000 for the United States Army Air Corps. Ford initially accepted. Engineers began examining the Merlin drawings. Prototype work commenced at the company's facilities. But then, abruptly, Henry Ford withdrew. The official explanation was that Ford would only produce military equipment for American defense, not for foreign nations. The unofficial explanation was more complex. Ford harbored isolationist sentiments. He had accepted a Nazi medal in 1938. His anti-war stance was well documented. Whether his decision was political, practical, or personal, the result was the same. Britain's best hope for expanded Merlin production had collapsed. Enter Packard. The Packard Motor Car Company of Detroit built luxury automobiles that many considered the American equivalent of Rolls-Royce. The company had experience with precision engineering, large displacement engines, and the kind of manufacturing tolerances that the Merlin demanded. Packard also built the powerful V-12 marine engines that powered American PT boats. When Lord Beaverbrook's representatives approached Packard in June 1940, the company's management saw an opportunity to contribute to the war effort while keeping their skilled workforce employed. The negotiations moved quickly. By September 1940, an agreement had been reached. Packard would receive the engine drawings, sample engines, and technical support from Rolls-Royce. Britain would fund the construction of a new factory in Detroit specifically for Merlin production. In return, Packard would produce engines for both British and American use. The contract value was $130 million, an enormous sum in 1940. If you are finding this story as compelling as I believe it deserves, take a moment to subscribe and ensure you do not miss the dramatic chapters still to come. The transformation of the American aviation industry is about to intersect with British engineering genius in ways that would change the course of the entire war. The technical challenges facing Packard were extraordinary. The Merlin had been designed using British engineering standards, which differed in fundamental ways from American practice. Every drawing used third-angle projection, while American engineers worked in first-angle projection. Dimensions were specified in imperial measurements that did not precisely match American standards. Tolerances were defined using British gauge systems. Before a single engine could be built, Packard's engineering team, led by Colonel Jesse Vincent, had to effectively translate the entire design into American manufacturing language. More significantly, Rolls-Royce had designed the Merlin for production methods that relied heavily on skilled craftsmen. Individual components were hand-fitted during assembly. Experienced workers made constant small adjustments to ensure everything meshed perfectly. This approach produced excellent engines but limited production rates. Packard's philosophy was different. American mass production demanded interchangeability. Any component should fit with any other component without modification. This required tighter manufacturing tolerances than Rolls-Royce had ever attempted. The process of Americanizing the Merlin took months of intensive work. Every component was examined, remeasured, and redimensioned to American specifications. New tooling was created. Assembly procedures were redesigned for production line efficiency. The first Packard-built Merlin ran on August 2, 1941, during a special ceremony at the Detroit plant. Full production began in 1942. What emerged from the Packard factory was designated the V1650. It was, in essence, the same engine that Rolls-Royce produced in Britain. The cylinder dimensions were identical. The supercharger design was unchanged. The fundamental architecture remained pure Merlin, but the manufacturing quality exceeded anything that had come before. American mass production techniques had produced components with tighter tolerances and more consistent quality than even the craftsmen at Derby could achieve. When Rolls-Royce engineers examined Packard-built engines, they were forced to acknowledge an uncomfortable truth. The Americans were building their engine better than they could build it themselves. This acknowledgement was not easy for the British engineers to make. The Merlin represented the pinnacle of British achievement, a product of decades of accumulated expertise stretching back to Henry Royce himself. To see Americans take their drawings and produce superior results challenged fundamental assumptions about British engineering excellence. Yet the evidence was undeniable. Packard's quality control systems caught defects that would have passed through British inspection. Their assembly procedures ensured consistency that hand-fitting could never match. By the end of the war, Packard had produced 55,511 Merlin engines for the United States Army Air Forces, with an additional 797 built by Continental. British production across all factories totaled approximately 149,000 units. The American contribution was substantial, representing roughly a quarter of total worldwide Merlin production. Without those Packard engines, the Allied air campaign would have been significantly diminished. The question of whether America stole the Merlin cannot be answered simply. The technology was licensed, not taken. Rolls-Royce received payment for every engine Packard produced. British engineers provided ongoing technical support. The arrangement was a partnership born of desperation, undertaken because Britain alone could not build enough engines to win the war. Yet there is another perspective. The Merlin represented decades of British investment in research, development, and refinement. The two-stage supercharger that made the Merlin 60 series so exceptional was pure British innovation, developed by Stanley Hooker and his team at Derby. When Packard built their VB 1653 and VB 1657 variants, incorporating these advanced features, they were producing British intellectual property using American methods. The profits flowed to an American company. The production expertise remained in America after the war. The jobs were American jobs. The marriage of Merlin and Mustang represents perhaps the most consequential application of this technology transfer. The North American P-51 had been designed to a British specification in 1940. Originally powered by an Allison V1710 engine, the early Mustang showed promise at low altitudes but suffered above 15,000 feet where the single-stage supercharged Allison ran out of breath. The Royal Air Force used these early Mustangs for ground attack and reconnaissance, roles where high-altitude performance mattered less. Ronald Harker, the same pilot who had nursed his damaged Spitfire home across the Channel, was now a test pilot at Rolls-Royce. In April 1942, he flew an early Mustang and immediately recognized its potential. The airframe was exceptional, aerodynamically clean, with a laminar flow wing that reduced drag to levels no other fighter could match. Range was extraordinary, nearly twice that of a Spitfire. But the engine was wrong. Harker wrote a report recommending that the Mustang be fitted with a Merlin 61. Resistance was immediate. The Air Ministry had allocated all Merlin 61 production to Spitfires, Lancasters, and Mosquitoes. There were no engines available for an American aircraft that the RAF had relegated to secondary duties. Harker persisted, pushing his recommendations up the chain of command until they reached Air Chief Marshal Wilfred Freeman. Freeman understood what Harker was proposing. A Merlin-powered Mustang could escort bombers all the way to Berlin and back, something no existing fighter could accomplish. 5 Mustangs were converted to Merlin 65 power in Britain, designated Mustang X. Trials at Rolls-Royce's Hucknall Airfield confirmed everything Harker had predicted. Maximum speed increased by over 50 miles per hour. Rate of climb improved dramatically. High-altitude performance transformed from mediocre to exceptional. But Britain could not proceed with production. Every available Merlin was already committed. The solution came from America. North American Aviation modified two P-51s from their production line to accept Packard F-1653 engines, the American-built equivalent of the Merlin 61. These aircraft, initially designated XP-78 before being renamed XP-51B, first flew on November 30, 1942. The results were spectacular. Maximum speed reached 440 miles per hour. Service ceiling exceeded 40,000 feet, and with additional fuel tanks, range extended to nearly 2,000 miles. The P-51B entered production in 1943. The improved P-51D, with its distinctive bubble canopy providing better visibility, followed shortly after. Together, these Merlin-powered Mustangs would sweep the skies of Europe clear of the Luftwaffe. Their ability to escort bomber formations all the way to targets deep inside Germany and back changed the entire strategic air campaign. Previously, American bombers had suffered catastrophic losses on missions beyond fighter escort range. Now they flew with protection from takeoff to target and home again. The impact on German fighter forces was devastating. Between January and April 1944, the Luftwaffe lost over 1,000 fighter pilots, including 28 with more than 30 confirmed victories and 8 with more than 100. These irreplaceable experts had been the backbone of German air defense. Once they were gone, the quality of Luftwaffe resistance declined dramatically. American and British bombers could strike German industry with increasing precision and decreasing losses. The Merlin-powered Mustang did not just escort bombers, it systematically destroyed Germany's ability to contest control of its own airspace. The efficiency advantage of the Mustang was remarkable. Author Jeffrey Ethel calculated that the P-51 achieved 3.3 miles per gallon of fuel compared to less than 1.8 for the P-47 Thunderbolt. This fuel efficiency, combined with the Merlin's reliability and power, gave the Mustang what Brigadier General Thomas Haze called the three qualities you need most for escort missions: range, range, and range. American pilots quickly came to love the Mustang. It was fast, maneuverable, and possessed excellent visibility from its bubble canopy. The Merlin's distinctive sound, a throaty growl that deepened under power, became the soundtrack of American air superiority over Europe. Yet every time a Mustang pilot pushed his throttle forward, he was relying on British engineering built to British specifications, refined by British mathematicians like Stanley Hooker. The Lancaster bomber represented another crucial application of Merlin power. Avro's four-engine heavy bomber carried the RAF's strategic bombing campaign to German cities and industrial centers. Each Lancaster required 4 Merlins, making it the largest single consumer of the engine. The bomber could carry 14,000 pounds of bombs over 1,600 miles, striking targets deep inside enemy territory. When the RAF needed to destroy specific high-value targets, the Lancaster was the weapon of choice. The famous Dambusters raid of May 1943 employed specially modified Lancasters carrying Barnes-Wallis's bouncing bombs. The attack on the Ruhr dams required extraordinary precision, flying at low altitude through heavy defenses. 8 of the 19 attacking aircraft were lost, but the bombs successfully breached 2 major dams, flooding the industrial Ruhr Valley. Every one of those Lancasters was powered by 4 Merlin engines. The success of the raid and of the entire RAF bombing campaign depended on the reliability and performance of that remarkable engine. The de Havilland Mosquito demonstrated yet another aspect of the Merlin's versatility. This remarkable aircraft, constructed largely of wood to conserve strategic metals, was powered by 2 Merlins and could outrun virtually any German fighter. The Mosquito served as a night fighter, photo reconnaissance platform, precision bomber, and pathfinder for larger bombing raids. Its speed and altitude capability made it nearly immune to interception. German fighters simply could not catch it. By war's end, the Merlin had been fitted to over 40 different aircraft types. Its evolution from the 1,000-horsepower engines of 1938 to the 2,000-horsepower variants of 1945 represented an extraordinary engineering achievement. The basic architecture remained unchanged, yet continuous refinement had doubled the power output while improving reliability and extending service life. Few engines in aviation history have demonstrated such development potential. The relationship between British design and American production continued to generate controversy long after the war ended. Some British commentators argued that America had exploited the desperate circumstances of 1940 to acquire technology that would otherwise have remained exclusively British. The Packard V-1650, they noted, gave American aircraft manufacturers access to the world's best aviation engine without the decades of investment that Rolls-Royce had made to develop it. American perspectives differed sharply. Without Packard production, they argued, there would not have been enough Merlins to power the aircraft needed to win the war. American industrial capability had taken a British design and produced it at volumes and quality levels that Britain alone could never have achieved. The collaboration had saved lives on both sides of the Atlantic. To characterize it as theft ignored the mutual benefits and the wartime necessity that drove the arrangement. The truth, as always, lies somewhere between these competing narratives. The Merlin was unquestionably a British achievement, built upon the genius of Henry Royce, refined by Stanley Hooker, and produced through the efforts of thousands of British workers. The decision to license production to Packard was made under extreme pressure when Britain's survival was genuinely uncertain. America provided something Britain could not produce itself: the capacity to build engines fast enough to win the war. What cannot be disputed is the Merlin's central role in Allied victory. Without it, the Battle of Britain might have been lost. Without it, the strategic bombing campaign would have been impossible. Without it, the Mustang would have remained a mediocre performer, relegated to secondary duties. The engine powered the defense of Britain, the bombing of Germany, and the establishment of air superiority that made the D-Day invasion possible. Mike Evans, founder of the Rolls-Royce Heritage Trust, summarized its significance simply: "Without the Merlin, we would not have won the Battle of Britain, and Hitler may have crossed the Channel." That assessment is not hyperbole. It is a sober evaluation of historical reality. The engine designed by Henry Royce's successors, refined by Stanley Hooker's mathematics, and produced in both British and American factories, changed the course of the 20th century. The legacy of the Merlin extended far beyond the war years. Rolls-Royce used the expertise gained from its development to become a global leader in jet engine technology. Stanley Hooker himself moved from superchargers to turbines, playing crucial roles in the development of engines that would power the Concorde and countless military aircraft. The knowledge base created during the Merlin program became the foundation for British aerospace preeminence that continues today. Packard did not fare as well. The company's automotive business declined after the war, and it eventually merged with Studebaker before disappearing entirely. But the production techniques developed for the Merlin influenced American manufacturing for decades. The precision required to build aircraft engines pushed American industry toward higher standards of quality control and measurement accuracy. The aircraft themselves became legends. The Spitfire remains perhaps the most celebrated fighter of the Second World War, an icon of British resistance and technological achievement. The Lancaster is remembered as the sword that struck at the heart of German industry. The Mustang, combining American airframe design with British engine technology, represents the productive power of the Allied partnership. Each of these aircraft owed its capabilities to the engine that powered it. The human stories behind the Merlin are equally remarkable. Henry Royce, the self-educated engineer who rose from poverty to create one of the world's great manufacturing companies. Stanley Hooker, the mathematician who applied academic theory to practical engineering and transformed the engine's capability. Ronald Harker, the test pilot, whose persistence ensured the Mustang received the engine it deserved. The thousands of workers in Derby, Crewe, Glasgow, and Detroit who built engines under extraordinary pressure, knowing that lives depended on their work. These individuals and countless others whose names history has not recorded created something that transcended mere machinery. The Merlin was not just an engine. It was a symbol of resistance, of ingenuity, of the determination to prevail against overwhelming odds. When young pilots climbed into their cockpits, their confidence rested partly on the knowledge that the Merlin would perform when they needed it most. That trust was earned through years of development and millions of hours of reliable service. The sound of a Merlin engine is unmistakable, a deep, resonant rumble that rises to a roar under power. At air shows around the world, that sound still moves audiences to tears. It evokes memories of sacrifice and triumph, of a time when civilization itself hung in the balance. Those who heard Spitfires scrambling during the Battle of Britain, or watched Lancasters departing for night raids over Germany, or witnessed Mustangs streaking across the sky above occupied Europe, never forgot that sound. Was the Merlin stolen by America? The question itself may be too simplistic. The engine was shared, not stolen, under circumstances where Britain had no better alternative. America provided manufacturing capability that Britain desperately needed. The arrangement was imperfect, driven by necessity rather than mutual preference. Both nations benefited. Both nations contributed. The victory that resulted belonged to both. What remains beyond dispute is the Merlin's place in history. It was, by any reasonable measure, one of the greatest engines ever built. Its combination of power, reliability, and development potential set standards that few other designs have matched. The decisions made about its production, including the controversial American license, shaped the outcome of the Second World War. If this story has captured your imagination, if you want to understand more about the engineering marvels and human dramas that shaped our world, subscribe to this channel. History is not just about dates and battles. It is about the people who created the technology, made the decisions, and flew the missions that determined the fate of nations. The Merlin engine stands as proof of what human ingenuity can achieve under the most demanding circumstances. Its legacy deserves to be remembered, studied, and honored. The next time you see a Spitfire at an air show, or a photograph of a Lancaster over Germany, or footage of Mustangs escorting bombers to Berlin, listen for that distinctive engine note. That sound is the voice of the Merlin, speaking across decades, reminding us of what was at stake and what was accomplished. It is the sound of British genius, American industrial power, and the Allied partnership that saved the world from tyranny. And that is a story worth telling, worth remembering, and worth understanding in all its complexity.